When it comes to rational inequalities, and I just wrote that one as a representative, you have any number of ways you could write it. But when it comes to these sorts of things, really the process is more or less the same, except that we also want to be careful about what happens when q is equal to 0. Because points where q is equal to 0, those might be those jump things, those might be the holes in the graph, those might be asymptotes. There are a whole bunch of ways that the function can very suddenly and violently change its behavior at such a location, so we do have to be a little bit careful about them, and when we're talking about our potential boundary points, we have to include those as well, but we'll see what that looks like with another example. For this, we want to solve and graph the solution set of the rational inequality 2x over x plus 1 is at least 1. Where here, we can start this by rearranging slightly. We will take the 2x over x plus 1 and pull over the negative 1 to get that 2x over x plus 1 is at least 0. And then we're going to have to rearrange this a little bit more because dealing with it in terms of these split terms, it's not very convenient. We want to get that whole thing into one rational so we can actually easily identify what types of things we're looking for asymptotes and 0 points. So I'm going to find a common denominator here. That means multiplying this guy by x plus 1 over x plus 1. So we will have 2x over x plus 1 and then minus x plus 1 over x plus 1 is greater than or equal to 0, or 2x minus x plus 1 over x plus 1 is greater than or equal to 0. And from here, we'll factor in the negative, so that would be a minus x. We would get x, and then minus a plus 1, minus 1 over x plus 1 is at least 0. And from here, for one, it's a little bit cleaner, and two, it's pretty easy to notice what our boundary values could possibly be, what values we're looking for. Here, this is 0 when x is 1. That is 0 when x is minus 1. So our potential boundary values, which I didn't notate in quite this way in the last example, but that's okay, are at x is equal to plus or minus 1, which means if we want to think about our intervals, we need to be a little bit careful here because negative 1 can't be an option for the fact that that's a place where this thing doesn't exist at all. You have a division by 0, and no matter what you do with an inequality, it's still a problem. But because we have a non-strict inequality here, 1 is valid. So we need to be aware of the fact that 1 is a potential point that can be included if it's in one of the intervals from negative infinity to negative 1, or negative 1 to 1, or 1 to infinity, as we have pictured like so. And then for this, we need our test values yet again, where I'm going to try and be a little bit more economical with my space here. In our first potential case, we are trying to go from negative infinity to negative 1. So we don't have any great options there. I'm going to pick x is equal to negative 2 because that's close. And if we take x is equal to negative 2, then what we will end up with is negative 2 minus 1 over negative 2 plus 1, which ends up being negative 3 over negative 1, or 3, which is positive. So we will have that our function is positive on that interval. It's always bigger than 0 on that part. Then we might get our potential change, where you could also have that it turns around there. Any number of things happens at negative 1 because that's division there. In particular, that's going to be something asymptotic because it's not a factor at the top. But anyway, pick a value. We can use 0. We should use 0. I'm going to check what happens when x is equal to 0 for that middle interval, which means we're going to look at 0 minus 1 over 0 plus 1, or, well, negative 1, which is definitely less than 0. So on this interval, f is going to be negative. It's always going to be negative all through there. And then our last chance, our last place to check is from 0 and beyond, where again, don't have any obvious candidates. If you don't have obvious candidates, just pick something close. X equals 2 works, where we would have 2 minus 1 over 2 plus 1, or 1/3, which is importantly bigger than 0. It doesn't actually matter what the function value is. What matters is that it's positive. Where because it is positive, the whole function is positive on that interval. And because it is positive on that interval, that means that each of these is part of our potential solution set. So if you want to write out our solution set, what we would have is the interval from -infinity to -1, union, so along with the half-open interval from 1 to infinity, where we include 1 because of that non-strict inequality there and the fact that 1 is valid. We can't include -1 because -1 isn't a valid value to satisfy any sort of relationship because you'd be dividing by 0. And that's how we'd get our answer here. So the process is, like I said, basically the same, except for a small but very, very important subtlety. And we'll finish this section, we'll finish this chapter, we'll finish this unit with one more applied example.